Okay, so I can start, and my goal today is try to explain something about the connection of two things. The one thing is a representation of surely simple vertex operator algebra, which we have. It is calling, what we are talking is simplest lattice vertex operator algebra. This is one part of a story. And second part of a story is what I explained in second half of the previous lecture. So it was fusion of fusion type constructions. Well, so I want today precisely trying to precisely formulate what is related with what, and in several examples. And my main example in vertex operator algebra side is the following things, that I take Clifford algebra or algebra of fermions, and I recall that the E1, it is psi z and psi star z, and psi z is the sum psi I z minus I, psi star z is the sum z minus I, and algebras. We discussed even in some details yesterday the representation R, irreducible representation of this algebra, and this irreducible representation, it was the direct sum of vector space V, where vector space V has a basis EI, I belongs to Z, yes, and basis in this space is the space of semi-infinite forms. Typical example is this. Yes, and there we have an action of this and that, and this I explained. And the next example was following, that I have two copies of this. I mean psi1 z and psi1 star z, psi2 z, psi2 star z. Yes, and maybe I put yesterday this is here. Yes, and or, for example, psi3 z and psi3 star z, and I can take n copies of them. For example, for 3, I could take, it mean I consider a bigger algebra, which is Clifford algebra generated by this, and I can take in this algebra subalgebra generated by psi1, psi2, psi3, all depending in Z, and also the same with the star. And also 3 here. And for example, in this case, I was denoted by GZ, and this denoted by QZ. And I claim that in this case, the corresponding, we can consider the algebra we generate by this and this. And I said that, for example, this is rather famous and popular example because this is n equal to algebra. And we can do more than that. We can take many copies, take products like this and form some version of G and Q. And then let us examine a little bit this example. So what is going on, as I said? So we have some algebra with such kind of generators, and let us consider GZ. GZ is the sum of GI, Z minus I, and, who are J? If we look to this expression, it means that GI is the sum psi1 alpha, psi2 beta, psi3 gamma, alpha plus beta plus gamma equal I. This is more or less by definition, or we take just this expression, write down each psi is equal by this, and just formally make a product, and then it gives us such operators. So, and let me repeat or just formulate again what we know about this operator GI. We know two things. One thing is that GI, GG plus equals 0 because they're fermions, Q-symmetric things, and we have a product of 3. But we know a little bit more. We know that 2 it's some relation which from this formula, if I write down it like this, then what I can do? I can write down GZ times G prime Z. And if you formally write down what does it mean, G prime, you take this expression and differentiate it by Leibniz rule, and if you take a product, then surely we get 0. Because psi times psi, this is fermion, and this is 0, and at least it is true formally. But actually, not formally, but literally. It means that the corresponding GI, they satisfy the condition which is here, follow from here. And if you look it in component, this is what? It is the sum of G alpha times G beta times alpha minus beta and alpha plus beta equal any S. Such kind of sum is 0. And we also discussed several times the condition that if we have this, then the correlation function or matrix element of corresponding operators, they satisfy some condition. And condition is that correlation function that G Z1, maybe T in my usual notation, and G T2, and any matrix element here like this. It is skew symmetric in T1 and T2, and it's more than that. Skew symmetric function, it is polynomial, and skew symmetric polynomial is 0 on that diagonal, but this has extra condition that it is 0 on the diagonal more. But if a skew symmetric function, it is, because it is skew symmetric, it is T1 minus T2 some power, and in this case, it is cube times something. So again, from this condition, it follows that this matrix element is T1 minus T2 cube times some polynomial in T1 and T2, and this polynomial is symmetric, and all object is skew symmetric, and this is property. And so main idea of vertex operator algebra is that we can look to this condition, or we can write down this condition, and they are the same. Now, suppose we just want to discuss some algebraic consequence of these conditions. What does it mean? And what it gives us? That the exercise which I want to discuss now, that no, we had some construction, and this construction gives us GI, which is satisfy this condition. But now we want to go by an opposite way. It means that I take just algebra generated by G alpha, and the alpha belongs to Z. And I want to consider the representation of just this algebra, but just impose some condition to highest weight vector. Anyway, here alpha belongs to Z. Suppose I have representation of just algebra which satisfies such relation, and also skew symmetricity, surely. Suppose I have vacuum vector which sometimes I identify with 1. Then, and my condition was that G alpha is 0 if alpha is non-negative. Therefore, if it is this condition, then I can generate new vectors by G minus 1, G minus 2, and so on. And corresponding space which I generate, this is what? This is vacuum vector, but it is G minus 1, GI1, GI2, GI3, and so on, times vacuum vector O1. It will be all I which I here are from here, they are negative, and it will be some space. But we'll also have to see, no, if they are just skew symmetric, it means that so skew symmetric, but no, this relation is not hold, then in this case, the corresponding representation is just monomial of such, has a basis monomial of such structure where these indices can be equal because fermion square of each element is 0, and they are skew symmetric, so it means that E1 is bigger than E2, bigger than E3, and so on. And so, but this is in the case when but what actually follows from this relation? Well, let us look to this relation. Suppose here S is what the simplest way. So suppose that S is odd, and S is equal to M plus 1. Then this relation, what is this? It is Gm times Gm plus 1. Yes, and the difference is minus 1 in this case, maybe minus in front. And then plus, we have 2 Gm minus 1. No, here 1. And here maybe 3 we have. M minus 1, M plus 2, plus so on. And yes, and if S is equal to 2M plus 2, then relation is looking how? We have Gm times Gm plus 2 plus. And here, because of this, we have minus 2 here. Next term is Gm minus 1, Gm plus 3. Then we have 4 here, plus so on. So our relation are looking like this. And using this relation, what, from the point of view of the basis, it means what? That if in the basis we have element like this, we can rewrite it as a sum of elements here, because this sum has to be equal to 0 from the relation, and these things also has to be equal to 0. Therefore, from the relation, we have conclusion that if I consider the representation which I am talking about here, then in this representation, the elements G alpha I1, Gi2, Gi3, and so on, times vacuum vector O1, they span the space, but about these things, they are negative numbers, and this is the biggest, this is smaller, 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 smaller. So I1 bigger than I2, bigger than I3, bigger than so on, but more than that. If, for example, I1 equal I2 plus 1, then using this relation, I can rewrite the corresponding monomial. And if it is 2, then using this relation, I can rewrite this monomial. Therefore, my conclusion is that this is true, but more than that. Then E alpha is bigger than E alpha plus 1 plus 2. Yes, or it means that the basis in my node, still about basis we do not know now, but at least still, but we know that our space is spanned by what? So this I running in the minus 1, minus 2, minus 3, and so on. And I have to consider the configuration like this. Suppose this is equal to minus 1. According to this, this is not available because I can, such product I can rewrite. This is also not available, but it is possible. Or this is possible. Anyway, next can be this. And this distance in this case is 3. this is 3, or it can be bigger. For example, here it can be like this. Here distance is 4, and so on. Now you can ask no, this is the question from elementary. No, this algebra is not very elementary, but at least the formulation is elementary. You just take a skew-symmetric algebra, in this case generated by g minus 1, g minus 2, g minus 3, and so on, and factorize it by quadratic relations. And this quadratic relation in this case has such form. And we can just asking what is this? How many elements survive in this Grassmannian algebra after factorization? And easy part, even this I do not explain fully, but I think more or less it is possible. It is understandable that at least such kind of monomial spans all space. But we cannot be sure that there are no relations between these monomials, because in principle, who knows? We can use this relation, we can start to rewrite using this relation, and it is possible so that some linear combination of these monomials is 0. And this, well, here let me just formulate just some problem from pure algebra. I have not time to discuss it, but it is interesting because suppose we are generalizing such kind of question a little bit, that we have just algebra generated by g minus 1, g minus 2, g minus 3, and so on, and we factorize the skew-symmetric and generate Grassmannian algebra, and I factorize it by quadratic relation, and each quadratic relation has the following structure. It is the sum of g alpha, g beta, here some function in alpha beta, alpha plus beta equal s, and about this function we know that this is skew-symmetric in indices alpha and beta. Like here, no, we need it because it is skew-symmetric. And if you just have such relation that such kind of arguments working, and after factorization, it will be something where at least if mild condition to f, maybe even no condition, that such kind of monomials are span the quotient, but if you want such monomials be base there, then such f are not generic at all. And some strong condition, and if you want, you can just ask a question, what has to be here if we want such kind of basis, and then I want to formulate that if f alpha beta is alpha minus beta, then it is really true. Unfortunately, the proof is, in this case, is not very complicated, but it needs some technique. Maybe I will have time to say it today, maybe not, but at least Now, please believe me that it is true in this case. And there are some other examples which are, can be expressed in terms of elliptic functions. In general, when it is happening, this is not known. Anyway, in a quotient, I have a basis now. No, we believe that this is true, and I want to use it. So my problem is following. I have a skew commutative algebra generated by GI with a relation which I always till this moment work with, and I have a representation of this algebra. Let me call this representation R0. This 0 means that highest weight vector here, V, is killing by, so G0, G1, G2, and so on, such kind of elements are killing the highest weight vector, and this is 0. No, and because my algebra is skew symmetric, it means that on this representation, these elements are acting by 0, and who is really acting is remaining things, so G minus 1, G minus 2, and so on. Yes, and let us look to this representation. In this representation, I have one highest weight vector, and the first non-trivial things which is acting here. I can act by first component here. This is G minus 1. And so it gives me this vector. Well, and from the relations, we can see that if I take this vector, then this V times, if I act by G minus 1, no, and surely G minus 1, again, it is 0 because they're skew symmetric, but also G minus 2, G minus 1, V is 0. This is follow from my relation, and also G minus 3, G minus 1, V is also 0. Therefore, if I take this vector, it means that which G kill this vector. This G kill G minus 3, G minus 2, and surely G minus 1, and G0, and so on. Therefore, if I use the notation that R may be beta, this is a representation with the following data. So this representation, beta, is beta I use for the first component, which is killing highest weight vector. Definition of R beta is following, that it generates by V, and I know that G beta plus 1, and so on, they are killing highest weight vector, and all other G generate new things. And for example, this special vector, what is killing to this is minus 3. Therefore, we have a map R minus 3 to R0. highest vector from here going to here. From, no, we know that this is homomorphism because this is defined by the condition who kills the highest weight vector. And here we just find the vector, which is this, which is the annihilation condition is the same. So we do not know, we know that this is a map or a homomorphism of representation, but what we do not know, then this is embedding. But if you look to, if you believe in condition that if this is true and if you believe in condition in monomial basis, from this it follows that really this is embedding. I want to say that this is also some problem for algebra, and the fact that it is embedding, it cannot be completely trivial. This is, no, it is, if you're trying to think a little bit, then it is possible to prove, but it is not trivial. And then, but we can continue this. Continue, it means what? It is, here we have embedding R minus 6. Here we have embedding R minus 9. And so on. And also we can continue this in the opposite direction. I can write down this R3, then R6, and so on. And so we will get a representation of my algebra and such kind of embedding. And what I'm interested in that, so it's R3, then next R6, next it is R9, and so on. Now let me formulate what we get. So if we have such kind of embedding, then we can ask, can we make up a limit in this direction? But, and if yes, then the limit has to be some representation of algebra with generators GI and such kind of relation. And, well, and actually, this kind of problem about the limit has the interesting answer. And this answer is following. First of all, as I said, that in space, in this space, basis is labeled by what? It is labeled by configuration on a line with configuration of points. No, it's monomial. Monomial is enumerated or labeled by positions. So monomial, to say monomial, it means that in this case it is -1, -2, -3, and so on, and I put crosses here, which this distance is 3 or bigger than 3. Yes, and in combinatorics, if you have condition of such sort, then you can ask the following question. Can we form something like the semi-infinite configuration with this condition? So the semi-infinite configuration with well, I said that if we have the space of semi-infinite forms, then the basis in the space of semi-infinite forms is labeled by what, as I explained? Some semi-infinite configuration here. I put some crosses here, actually infinite amount of crosses, such that they are finite in this direction. And here in this direction, after some moment here, for example, in this case from 3, it is going like this. But now, it was before, but now I change a little bit this situation, because now combinatorially my condition is different. So it means that we have also crosses, but it cannot be very close. It is some repulsive condition. They do not like each other. They want to be in a distance, in this case, 3 or more. Then the similar story is following. We can consider the space of configurations. On a line, which with similar properties is here. So it is, first of all, crosses can be only on distance 3 or more. Also, in this direction, this configuration is finite. And in this direction, the configuration is dense. So it means that after some point, maybe 5, for example, they are going like this. So usually we are saying that such kind of configuration stabilize on a tail in this direction and stabilize to 0 on that direction. Yes, and then what actually I claim that the direct, this projective, no, it is in injective limit. So so you see, I claim that this is subspace here, this is subspace here, and so on. But this is subspace here, this is subspace here, and so on. So there are the spaces which become bigger, 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 and in the limit it gives me something. And this something, about this something, it is a limit of what we had here in this direction. And the statement is that this limit, it has a natural, no, natural is surely not exact thing, something, but really it is natural. It is natural base. And these bases are labeled by configuration of such sort. Well, maybe it is reasonable to say one thing. In this case, no, because it is some repulsive condition that these crosses do not like to be too close to each other, then we have, in principle, 3 different tails. Because it depends, because this is 3, 3, 3, 3, so in this it can start with 0, it may be 3, 6, and so on. Or it may be 1, 4, and so on, or it may be 2, 5, and so on. And there are 3 different crosses, 3 different tails. And we have three different, in principle, we have three different spaces of such sort. If we look to this, it will be some special tail. And in this case, it is what? We saw it in principle, because what was this? We have highest weight vector here. The next one is G minus 1. It is going on here. The next one from this, it is going to G minus 4. But here we have G2. Here we have G5, and so on. It means I just, from the meaning of these points, they are calling here just extremal vectors. They're just top or generating vectors for all these R. And then, so we are going by this way. And, well, so in this case, tail is just this, 2, 5, 8, and so on. It is like this. And extremal vectors are corresponding to a possible dense configuration. So we have crosses. We take these crosses and we want to move it by this way in a most dense position. So from the point of the basis, they are corresponding to this space. What kind of, no, it is just some construction. Maybe one thinks why it is interesting. One thing is following. This is interesting because if we make up this construction, what we actually did, I take some algebra and generators as Q-symmetric, and additional relation are this, and I construct some vector space which has such kind of basis and so on. And if I make up the same construction using just only this relation and not this, then as a result, I get what was before the space what was yesterday like this. And no, it was a similar story. It means that I will find the basis, and this basis labeled by this such kind of configuration, but without this repulsive condition. But now we have such kind of condition by 3. And so I just construct this space. So when I did this, my logic was the following. So I start with a vector space with basis psi I. Then I suppose I belongs to Z. And then I make up some construction and so get this. But this construction gives us semi-infinite form. So I know that this object is the representation of Clifford algebra, where we have psi I and psi I star, where I have this psi I here acting by evident way, by product. And psi I star is not, even here is not completely evident. There are some operators which I explained erase the crosses and so on. And in this case, they give us a Clifford algebra. And the interesting element of a story is that if I do it with such a kind of G and make up the similar story, that as a result, I get some version of a space of semi-infinite forms with such dispersed basis. And then you can ask what algebra is acting on this space. What algebra is acting on this space, and before we had psi I and psi I star. Now we have GI, because we can product to GI. But what can be this? It is not the evident things, and a little bit astonishing fact is the following, that what I had before and how such things are appeared. Let me formulate this as a statement, but, well, I had three, psi 1, psi 2, and psi 3, all depending in Z. And I had also psi 1 star, psi, maybe I like T in this case. Yes, and I have generators G, which is psi 1, psi 2, psi 3, and I have generators Q, which is psi 1 star, psi 2 star, and psi 3 star. Yes, and in the corresponding space, in a representation of a Clifford algebra, I can choose the appropriate highest weight vector and act to this vector by GI and QJ. And my statement says that maybe, no, I can fix all constructions such that I get just this space. But maybe it is not important now. You can do, if you want, it by yourself. But the meaning of this statement, if you take highest weight vector, maybe W, highest weight vector, in the representation of this Clifford algebra, and then I act by algebra generated by G and Q, then I get precisely the vector space, this representation. So, no, this is possible to prove by direct checking, but if forget about the construction with psi, just make up this construction and trying to construct on this space the action, the analog of this, so the action of operators Qi. No, it is possible to do, but, and it is just a good question. Good because no simple solution. It is, just try to determine the action. No, well, so the problem is following, that I have a vector, after that, the resulting things which I want to understand better than I explaining, that I have some vector space. In this vector space, at least what I know, this is the basis. Basis is labeled by such kind of configurations which are stabilized to tail and so on. And then on this space, I want to determine as much explicitly as possible the action of operator GI which satisfy, which are skew symmetric and satisfy the condition which was there. And I wanted to determine the action of operator Qj, which are in some sense acting in the opposite direction, and they are also skew-symmetric and also satisfy the same condition. And then they have some relations. Yes. Anyway, this is our story, and now I want even about this to say a little bit more, but now let me discuss a little bit the question of connection of such kind of construction with the fusion construction. No, the fusion construction, it means that in such kind of algebra, there are some subspaces which, because of relationship with representation theory of affine algebra, subspaces, I want to call these subspaces by de Mazur subrepresentation or subspaces. Anyway, about de Mazur, if I want to say who are they, I need only my representation like this. I need to know that on this representation the operator Gi are acting. And I want to know that this operator Gi, they satisfy the relation, the quadratic relation, what was such relation I wrote before. Anyway, I explained that in this space we have external vectors. They are like this. And de Mazur representation, sub-representation, they're defined by which way? I take some external vector, W. W can be one of this external vector. And after that, I apply to this external vector the annihilation operator. More precisely, I want to act by algebra generated by operator G0, G1, G2, G3, and so on. And so what I can do, it is not interesting to apply this operator to this, and so on, because it is zero. For example, this vector, by definition, are killing by G0, G1, G2, and so on. And this vector is belong to the same space, because you see that R0, my R0 is a part of this space generated by this vector. And what was R3? It was something was generated by this vector. And what was R6 in my notation is what generated by this vector. So all these spaces are just one-dimensional, and let me forget about this, and I want to take this vector as a starting point. In this case, I cannot act by this, and this, and this vector remaining, and in this case, what I call de Mazur subspace is one dimension. Now look to this point. What I can do? I can act to this vector by G0, and I can act to this vector by G1, and so I get as a result this vector, and this vector. And not only that, you can take this vector and act by G0 and here by G1. It will not be 0. No, in principle, G0 times G1, using relation, we can rewrite, and it gives us this. Therefore, it is not 0. And so I want to say that the Mazur subspace will generate by this vector. This is one-dimensional here, then 3 vectors here, and then 1 vector here. Yes, and then a similar story appears if you start with this vector. So in this case, it will be what? I start with this vector, then it is 1, but here we have not 3, but 5 vectors. And no, not 5, but 6 vectors. I can act by 0, by 1, by 2, by 3, by 4, and it will be 6, and then it will be something. So we get sub-representation, and these sub-representations are representations of G0, G1, G2, G3, and so on. And no, I wanted to discuss this example, at least present to you this example, because it is simple but looks rather non-standard. Anyway, our space is, no, we define our space as the union of subspaces. That what was R here, it was, no, again, this is symbolically, this is what? It is some representation of my algebra generated by Gi. Then I take, in this representation, the property is what? That I have extremal vectors here, and the whole space was defined by what remaining here, by the union of subspaces which generated by this vector. So R0 is this, and there R3 minus 3 is this, and so on. And actually, this is subspace, the bigger subspace generated by this, bigger subspace generated by this, and my whole space is the union of these subspaces. But it is other way to describe the same space. If we look to this space, I have this vector, then I have something generate from here, then I have something generate from here, from here, from here, and so on. Yes, and these such kind of subspaces are, no, again, they become bigger, 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 and bigger, and all space is the direct limit of some such subspaces. Well, and then the fact that I think looking rather surprising is following. Now, about dimensions. Now it is 1. The next one is 5. But if again, on the end of my previous lecture, I can ask you about the dimensions which appear here. And no, surely you cannot guess, because it is rather complicated to continue sequence of numbers starting with 2. But at least in the end of previous lecture, we had something what was equal by Fibonacci numbers. And these Fibonacci numbers, what was they? 1, 1, 2, 3, 5, 8, then 13, then 21. Yes, and my subspaces, which appear here, dimension are following. It is 1, next 5, and next it will be 21. And next it will be, so what appear from this vector, it will be 21, and so on. And well, if you want to get the other Fibonacci numbers, this is also possible. And for that, you need to consider different tails. Now, for example, different tails, it means that I can considering something like this. Here acting G0, here is acting G minus 3, here is acting G3, and so on. Now, this is the same structure, but I just shift this numeration, and it means now my tail here tail 2, 5, and so on, and here tail 3, 6. And in this case, if you take, for example, this vector and act by G0, then we get this. Yes, and next space will have, say, this dimension. Next space has this dimension, and so on. And so all Fibonacci numbers appear as the dimension of subspaces. Yes, and now no, I did not formulate last time. I almost did it, but not precisely. Let me just say what kind of fusion construction give me just these spaces. And the construction is following. So fusion construction. This fusion construction is the skew-symmetric counterpart of last lecture. For that, let me do the following. I can take the polynomial ring in some coordinates, say z maybe in this case. It has basis 1, z square, and so on. Yes, and maybe I change notation, E0, E1, maybe, no, better use Greek letters, C0, C1, C2, and so on. Yes, and now, and this is V. And let me consider the Grassmannian algebra generated by V. So it is, in some notation, it is like this. Psi 0, psi 1, psi 2, and so on. Let me just take this skew commutative algebra. And after that, I can just proceed by the same way as yesterday. It means that I choose I choose some x0, x1, x2, and so on, xn minus 1. They will be some different numbers, and then I take so x0, x1, x2, xn, this is configuration space, configuration of points of a line. Let me fix them. First of all, I want to say that algebra, Grassmannian algebra psi0, psi1, psi2, and so on, it goes to exterior algebra of some generators B0, B1, and so on, Bn minus 1. I'm thinking that B0, B1, B2, and Bn minus 1, I think about them as some generators sitting in the points x0, x1, x2, xn. If I want to determine this map, what I do, I take psi and just saying that it is going on to the sum Bs times xs over I. Or it means that because this generating space, no, it is Q commutative algebra and then Grassmannian algebra. And if I can determine the homomorphism, I just can take these generators and send them to generate here by any way, and I choose this way. Or if I consider the space of generators FCZ, it just means that generator from here just function in Z goes to the sum of Bs times f of xs. Yes, and this is just the same. Anyway, it is a homomorphism of such sort. Yes, but after that, I take the representation. No, this is Grassmannian algebra. And it goes to I factorize it by ideal, which is generated by a product, bi plus 1, for any I. So it means that I factorize it by quadratic expression, quadratic monomials by 0 by 1 by 2, and so on by n minus 1 by n. And so, well, what actually we discussed yesterday? We discussed the same story, but for ring of polynomials. And in this case, if we apply the simple things which we discussed yesterday, then the dimension of this space, because it is Grassmannian algebra, is equal to power n, and the dimension of such quotient is equal to Fibonacci number. No, because we just count the number of monomials, well, look and this see what is this. And so if I denote this space maybe bar R like this, and then, so again, after that I can proceed by two ways. One way, I have a representation of Grassmannian algebra, And this representation of Grassmannian algebra is this. No, because it's homomorphism of algebras, and here I can act by the image. And then it is something, well, so as a result, I have some bundle living on a space of configuration of different points, and the dimension of this bundle is Fibonacci number. And fusion procedure mean that I want to send all different points to 0, and look what we have in a limit. And the corresponding things I want to call fusion, because these points are fused, and so it is this. Or I can go by a different way. Also here, what I can do. So my Grassmannian, let me just repeat. No, my Grassmannian algebra, this one, is graded because this is had grading 0, this is 1, this is 2, and so on. And Grassmannian algebra is the sum of graded space. And so inside this algebra, psi0, psi1, psi2, and so on, I have subspaces. By this I mean sum of graded component which are equal to 0, 1, 2, 3, and so on. It is M. So in this case, what we have, then 0, it is just 1 and psi 0. If I have, what is this? It is 1, psi 0, but we also have psi 1, and we have psi 0, psi 1, and no, and the elements of, if we have psi 2 somewhere or bigger than we're living in the bigger components, it is this. Therefore, anyway, in Grassmannian algebra, I have filtration, and if we construct fusion again by this way, it means in this R, I have 1 here, and then I can start to apply to this, in R, I have filtration. So first it is R0, then it is smaller R1, that it is R2, and so on. And again, at least without problem, we can see what is R0. Because R0 in R is 1, and I act by this. And so R0 is 1, and also the sum of all BI. No, because psi 0 is 1, and it is just this. And the R1 is this plus something. R2 is bigger, 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 and so then I can, I have R0 plus R1 over R0 plus R2 over R1 plus blah, 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 and it is so on. And by this way, I get some representation of Grassmannian algebra, which at least has dimension equal to Fibonacci numbers. And it is good to look in a simple case, what is this? Then if I want to compare with this picture, with this, let me take n equal 2. So it means that on this side, what I have? I have 1, I have B0, B1, and B2. And because I factorize, I have not this, I have not this, but I have also B1 and B2. And now if we look to what is going on, then surely I can act. No, what kind of filtration is this? It is starting with, no, I want to say that in this filtration, we will just see this part. As I said, the 0 part of filtration is this. Yes, the next part of filtration is this. I mean this, and this, and the last is the whole thing. And if you make up this explicitly, you find that we get such kind of story here. And if you want to get a piece which starts from here, you have to do it with n equal 5. We need to have 6 b, and it is not completely easy to do. No, in both sides of a story, this is a question how to study it. And no, I will try to say a few words, but I cannot really explain the details well. But maybe I will make some short break, but before, let me just say what is going on. Just a little bit summarize. So I have two kinds, in principle, even 3 kinds of construction. One construction, I take this my psi1, the psi2, the psi3, the, and a similar story with star. And then here acting algebra with generator G and Q, Z, and I take highest weight vector, generate sub-representation, and it gives me something, which I claim this representation of vertex operator algebra, things like that. Or I can use G and construct this by the how I explained, and in this case, the fact that this is coincide with this, it is maybe just not mystery, but at least something. But what is real mystery is that I can define the same space by a very different way. I can make up such kind of construction. So it means I can take 3b, then 6b, then 9b, and so on, and make up such kind of de Mazur-like representation. After that, I can embed them to each other and construct the whole space, whereby this way I have the action of G, but not all, but only positive. But still it will be the same, and this construction is very different, but it gives us the same story. Well, so let us make some, maybe 10 minutes, a little bit less, and then we can continue. Okay, and we are discussing this example, and then I want to no, because all day today I discussing this GZ and QZ algebra, and I said that this is actually n equal to super the algebra. So let me just explain a few things about it. So how really to calculate something. Let us return to the beginning of the story. It means in this case, no, again, the problem about the algebraic relation of this and this. But what actually we know? So GZ, this is the sum. No, it is psi 1, z, psi 2, z, and psi 3, z, and also QZ is psi star 1, z, psi star 2, z, and psi 3, z, yes. And let me, probably I will need it, but maybe not. So let me erase this. So let me explain how the technique with correlation function and so on is working. Anyway, our problem is following, that we have sum of gi, maybe z or z minus I is so gz, and we have the sum of qi z minus I, which is equal qz, and about g with itself we know, q with itself we know, but because this g and this q are product of three fermions, then the natural question is what? I want to find out what is gi qj plus qj gi. So it is plus, and no, and the answer is that using in principle any definition, it is possible to say what is this. Then how to calculate? first, suppose, let us first consider the simpler case. That let me, this is the case which I took because it is slightly less standard when it is 3. But let me take psi1 z and psi2 z, and let me take 2 of them for simplicity. And let me write EI is the sum psi1 alpha. Then it is psi2 beta. Alpha plus beta equal S, equal I. And Fj is equal to the sum psi alpha 2 star times psi beta 2 star here, alpha plus beta equal J. Yes, in this case, our problem is how to calculate. No, this is definition of this is definition of this, and first of all, EZ, which is the sum of EI z minus I, now it is, because there are 2, then EI, EJ, just usual bracket is 0, but because of this and this I mentioned, then the sum of E alpha, E beta, alpha plus beta equal E is also 0. But suppose we just have this, and our problem is again to calculate EI Fj. Yes. And the question is how to do it. No, in our equation, which I really want to discuss, it is 3, but surely it is good to understand first more simple case when there are 2. And well, no, it is not big problem to make up the calculation explicitly. So I have this, and then I can write down the product in 2 directions, and we get something. Yes, let me explain maybe if somebody in this room heard about what is calling usually spinor representation, then if you have spinor representation, then what is going on here, there, is very similar, and maybe it is good to explain how to do it. Well, but before it, let me ask some question before starting explaining something about spinor representation. So, well, we have this, and we have this. And when I calculate this, it means the result has to be some expression in terms of fermions, of, I mean, in psi and psi star. And question to you may be the following. What degree we expect? So you see, this has degree 2. This has also degree 2. This has degree 2 in psi. This has degree 2 in psi star. Then I calculate the bracket. The result will be some expression in psi. And what degree in psi we expect as a result? No, in the end, we want to calculate explicitly, but the question is how complicated is this? So what actually we get? And to understand it, let us simplify our problem as much as possible. Suppose we have, no, maybe somebody knows the answer. And what kind of expression appear? No. Let me ask you more simple question, and this simple question maybe is the following: that now it is some big sum, but let me consider the following simplification. Suppose I have AB and I have A star and B star. Suppose that they are fermions, so it means A square is 0, B square is 0, and AB plus BA is also 0. Then A square, B square plus B, this is the same. It's also 0, and squares is also 0, and then A star plus A star A is 1, B star plus B star B is also 1, and such on other things as zeros. For example, A B star plus B star A is 0. Then this is actually this AB is some piece of this. And what I want to say, I want to take AB and take this Q bracket, just bracket, no, usual bracket, this with this. And it is equal to what? How to calculate it? Maybe you try it to do, who never did it. No, the problem is that now we are going about some simple things, but maybe starting from tomorrow, I will talk about more complicated things because it will be the second part of my lectures. And then, but at least today, I want to talk only about simple things. And so let us try to calculate how to calculate it, what kind of calculation you have to do. So this is, by definition, it is a bracket, so it is like this. Maybe you try to do it right now. Again, if you can do it, you can easily do this. The problem is the same, but we have many psi and psi stars. But it is not a big deal. Basically, this is the same things. So What is this? No, relations are here, and again, what we have to do using the relation, we have to write it, trying to put A here, A, no, here I have this, and this. Here they are in different order. The idea is trying to put it in the same order, but using the relations. And after we make up this, then, no, if we have 0 here and here, then they are just equal. So this equal to this. If we have 0 here, then what we can do? We can, here, A star is in correct position, so we can move it here. No, the A we can move here, and B we can move here. And after that, no, after it's skew bracket, and it will be -1, but after we do it, they just coincide. So it will be 0. But in reality, we have some correction because we have 1 there. Therefore, answer will be not 0, but something else. But what? Okay, maybe it means I can do it by myself, but let us first do it by two different ways. First, directly, that I want to put here A in the first position, and so it will be minus A star, B star. Yes, and now what we have here, then first I can move this here. It will be A star, A, B star, B. After that, what I can do? I can, using this relation, no, because this is almost this up to 1. So it means that these things is what? It is A star minus A star plus 1. It is this. And about this, it is the same story. It is minus B star plus 1. Yes, so, and after that, what we have? I consider product this with this. And so I have this term and this term. And it appears with the sign plus, and here sign minus. And so the things of degree 4 disappear. But what remaining? The remaining thing is what? The remaining thing is this times this. It is minus B star plus this times this. It is minus A star. Yes, and so this is a result of a calculation, and we see something from that. We see that we take quadratic things with quadratic things. And then I calculate the bracket. And in principle, it can appear something of degree 4, 3 maybe even. But 9, no. We have only quadratic things. And no, in this case, yes, but if we write it in a different degree, in different order, we get, in principle, get some constant. So if we do it just by this way, we get just this. But in general, no, the fact that if we have something quadratic and something quadratic, that we cannot have terms of degree 4 and degree 3, it is universal things. And it will always be like this. And the fact is that in this case, you see, we have infinite sum, like this and like this. But if I take pair elements from here and pair elements from here, that surely it depends which pair I take. But when I calculate bracket, almost in all cases it will be just 0. But sometimes we get non-zero but quadratic terms. And without calculation, we can conclude that the result of this bracket has to be combination where one psi, maybe 1 or 2, and one psi star, maybe 1 and 2 appear, So the expression which we can have here, for example, psi1 alpha, psi minus alpha 1 star, for example, or some other combination of such sort. So at least I want to say that calculation is not very complicated, but let me say something which is playing a role here. Maybe it is what I explained today, because it is, if you never heard it, maybe can be useful. So what spinor representation? Spinor representation of not group. Group is more complicated, of Lie algebra. So which Lie algebra you will see, first, what I want to say, this is some generic things which we saw here. So suppose we have just vector space with quadratic form. And suppose we form the corresponding Clifford algebra. What is this? Here in V we take basis from here, and Clifford algebra is just algebra generated by these elements, V1 and so on, Vn with relation. V alpha times V beta plus, for any pair, it is V alpha times V beta plus V beta times V alpha, and this has to be equal number. Just scalar product of this element is matrix of quadratic form. And we just look what is in quadratic form in position alpha beta, and suppose it is C alpha beta, and it has to be equal to this number, C alpha beta. Yes, so this is the algebra, and the dimension of this algebra is 2 power n. And next thing, that which is just a generalization of what I said. Suppose we have from here, from Clifford algebra, V1 times V2, just product, and V3 times V4. And I want to calculate the usual bracket of this. Maybe let us try to generalize my calculation. So what is this? So no, it is also not big deal. So we have to do what? We write down V1 times V2 times V3 times V4 minus V3 V4 times V1 times V2. Then what is this? No, we have such kind of relation, and it means that we need to rewrite it and to put V1 in the first position, then V2 on the first position. and then comparing the corresponding results. And this is first step. Then, so again, what I'm doing, I need to rewrite this in correct order, and then the result subtract for this. So I start to do it. I write this. Next, I want to put V1 here. So it will be V1, V3, V4, V2. So minus, so what it is doing here, so it will be minus V4, V2. And here I have C1, 3. And this remaining, it is minus C3, V3, V2, C4, 1. Now V1 is in the first position. But then we need to put 2 here. Then, but we can do it in 2 steps again. Then it gives us V1, V3, V2, V4, and here minus. No, because it is this, it is V1, V3, and here we have C24, if I correct, minus, let me not write it, minus this. And then one more thing I have to do, and I get this term, and here it will be what? It is going here, so it will be V1. No, it will be this term. I do not want to write it. It will be V1, V4, C3, 2. Here. If I write correctly. So therefore, the difference is this and this. Is this I can erase, and minus is also here. This is the sum of these terms. So what we have? We have all pairs there. No, all pairs which change the order, you see. That if we want to go from this to this, it means 3 and 4 in correct order, 1 and 2 in correct order. But I have to move this here and this here. And 1 is going through 3 and 4, and 2 is going after that from 3 and 4 also. Yes, and then the result will be the sum of quadratic expressions like this, and with the remaining scalar product of elements. So therefore, what conclusion we can, after that, we can make up? The conclusion is following. We have Clifford algebra. And in the Clifford algebra, we have quadratic V alpha, V beta, and then V gamma, V delta. And the result, as I said, will be the sum of also quadratic expression. So this is the general story. Therefore, the quadratic expressions like this, they form the Lie algebra, but actually up to constant, because V alpha, V beta, and V beta, V alpha are different. But up to this bracket of two quadratic expression is also quadratic expression. Then this is the question, what kind of Lie algebra we get? Yes, and so let me see that we have n-dimensional space. And no, if we have basis V1 and so on, Vn, we know that V alpha square is this number. And we all are doing up to constants, but the interesting expressions are V alpha, V beta, then alpha less than beta. So the dimension of corresponding space is n and minus 1 over 2. And according to what I said, the quadratic expression form the Lie algebra of dimension n times n minus 1 over 2. And if you heard something about Lie algebra, do you know some Lie algebra of such a dimension? And yes, I think that in some sense, if you heard about Lie algebras, something that what the simplest examples of Lie algebras you know. Maybe so if we have n-dimensional space, then we have matrix algebra, which is usually denoted by GLN. It is the n times n matrix, and so this algebra has dimension n squared. And you have also algebra which is a Selenian. This is matrix with trace 0, dimension n squared minus 1. But it is also more algebra. One is orthogonal algebra, and other is symplectic algebra. For this, let us forget for a moment. But at least to define this, we need on n-dimensional space the skew-symmetric form, and orthogonal algebra consists in matrix or linear transformation of n-dimensional vector space A, which satisfies the condition Ax y plus x ay equals 0. Yes, and if such condition is held, then the corresponding matrix is Calling orthogonal and or skew symmetric. And then if we have, they form the algebra, and if you have one matrix with this condition, and for any vectors from here, then AB plus minus BA satisfies the same condition. Yes, and I claim that the Lie algebra which we get this is just this. It is just orthogonal algebra. Yes, and first of all, the dimension of skew symmetric matrix is equal n times n minus 1 over 2. And then I claim that such kind of construction give us the same algebra, and maybe it is good to understand why. Because what? Let us take some expression, V alpha times V beta. And let us take some element Vs. And let me calculate this bracket. Maybe, so now we are living in Clifford algebra, and now we are talking about more simple problem. We calculate the bracket of quadratic expression with linear. And maybe, can you say me what is this? More complicated things we discuss. Now let us go to more simple. And so what is this?
Sum of linear expressions.
Linear expression, yes. So it is, you are right. What we have to do? We have to do just the same thing, but with linear. So it means that what it is doing, it is send this, it is what? It is V alpha times C beta S maybe. Maybe minus or plus. You can minus V beta times C beta S. Am I right or sign incorrect? Right. No, here alpha and here beta gamma. And here opposite, here alpha. Now it looks better. So now we see that each such things M, suppose, it gives us some matrix which send Vs to such combination. So conclusion that any quadratic combination, no, such linear combination of this, M, give me matrix from V to V. No, this gives us this matrix with this sent to this. But in combination, give me some matrix from this to this. Yes, and after that, no, because this is, let us check this. How? that I take two vectors from here, v1, v2 from this, plus v2, v1 is some number. No, let us write it like this. Then, if I can use the Leibniz rule. So if I take M, v1, v2, plus v2, plus v2, v1, and by Leibniz rule, what does it mean? It means that I apply, no, if I take this, I apply to this, then I apply to this, plus this, plus this. And if you write Leibniz rule, you get explicitly the fact that corresponding linear transformation is skew-symmetric. This is just the same. Therefore, no, we can check, but maybe you can do it by yourself. What we get, that the quadratic expression form the Lie algebra, and this Lie algebra, we have mapped from this Lie algebra to the algebra of transformation of vector space, which preserve the corresponding quadratic form in a sense what was here. Yes, so it is good to the algebra of skew-symmetric matrix. And after that, it is not, if we have this in mind, then we can use it here. So I want EI quadratic, FI is also quadratic. And then I write down EIFJ, and it is also quadratic. Well, and now my space where, Clifford algebra, now, this is the space with the basis. No, bases are the same things, like here. Psi1 alpha, psi1 beta, psi2 1 star alpha, psi 2 star beta, and each EI gives me some transformation of this space. Fi gives me some transformation of this space. And surely their bracket is also give us some transformation of this space. And anyway, the Lie algebra generated by EI and Fi give us some transformation of this big space. And because, all space where they are acting is very big, and so it seems a little, we can afraid to make up calculation. But if we have action here, it is not a big deal. And this algebra is very controllable. And so we can do it. And maybe I just explain how this calculation is going on. And in principle, the students, yes, they have to make up something, some kind. They need to solve some problem or write down something. to get from me. And I want that from me that something can be useful for people here. And no, and well, what I can, what you can do, and one thing to finish this calculation, that it means that G is something rather simple, and you can calculate the Lie algebra which generated EI and FG. So it means you to calculate it, it means it finds this, and then finds the bracket of the result of this with EI and FG, and just look what is this. Yes, and no, the problem which with G and Q, it is not so much complicated, but technically a little bit more than that, because one of the easiest way to do it is following, that first you have this EI and FJ, and then you make up this calculation. Then you just add to this the third one. And you just writing that GI is the alpha some psi 3 beta. Alpha plus beta equal I. And QI is the sum of F alpha psi star 3 beta, alpha plus beta maybe equal J. Yes, and after, if you write this, the calculation, no, it is not great difference, but at least it is a little bit easier, because when you calculate, but you have to calculate first of all skew bracket, and you need this with this with this is 0, this with this, you know, if you make up this, and this with this you also know. And after that, the calculation become more handleable. Yes. Maybe it is good, maybe I do not know when, to arrange some kind of seminar and make up this calculation. This I do not know, but it can be useful. And anyway, maybe I stop now, and only I want to say that 2 lectures which I give, they definitely will be more complicated. And I use, no, I will, no, I do not want to say that it is absolutely senseless to come, but at least more complicated. Okay, let me stop.